Okay, so my name is Lael, and today I'm going to be going over Exam 2, Problem 1a, which is a solution prepared by diluting 76.3 grams sodium iodide in 545 grams of H2O, which yields a total volume of 576 milliliters, has a mole fraction of solute that is 1.65 times 10 to the negative 2, a boiling point of 100.956 degrees Celsius, and an osmotic pressure at that boiling point of 27.1 atmospheres. And we need to prove that all three of these statements are true. So first, we're going to solve for the mole fraction, which in this case is the moles of solute divided by the total moles of the solution, because we're finding the mole fraction of the solute. So first, we're going to find the moles of sodium iodide and the moles of H2O. And we're given the masses for those two substances in grams, so what we need to do is divide those masses by the molar masses of the respective compounds. So we're going to get 0.5090 moles of sodium iodide and 30.252 moles of H2O. And these are not to the correct significant figures, but I will round to the correct sig figs in the end. So first we need to find the total moles by adding the moles of sodium iodide to the moles of H2O to get 30.761 total moles, and that's going to be our denominator. So now we can divide the moles of sodium iodide by the total moles by simply dividing this value by this value to get 1.65 times 10 to the negative 2 as the mole fraction of the solute. And if we look back at the problem, we see that that's exactly what we were supposed to get, so that is correct. So the second component of this problem is to solve for the boiling point elevation. We know that the addition of a non-volatile substance such as a salt, which NaI is, will elevate the boiling point of water. So we know that the equation for the change in the boiling point is going to be equal to the Van Hoff factor, this I value, times the Kb times the molality of the solution. And we know that the Kb of the solvent, water, is 0.512 degrees Celsius per molality. So all we need to do is solve for the I value and the M value. First, we can solve for the I value, that Van Hoff factor. To do this, we need to look at what happens when we add sodium iodide to water, H2O, to create an aqueous solution. What's going to happen is this compound is going to fully dissociate into its component ions, Na plus and I minus. Since there are two particles in this dissociation, I is going to be equal to 2. Now we can solve for the molality. The molality is going to be equal to the moles of solute divided by the kilograms of the solvent, which in our case is going to be the moles of NaI divided by the kilograms of H2O. And we know that the moles of NaI are 0.5090. We calculated that in the previous part of the problem. And we know that the grams of H2O are 545. So we can easily find the kilograms from the grams by multiplying the gram value by the conversion factor to kilograms, which is 1 kilogram per 1,000 grams. So once we divide the numerator by the denominator, we're going to get 0.9339 molality. So now we can calculate that change in boiling point by simply plugging these known values into this equation right here. We have delta Tb is equal to 2, the Van Hoff factor, 0.512 degrees Celsius per molality, the Kb value of water, times 0.9339 molality. And that's going to give us 0.956 degrees Celsius. But we're not quite done yet. We still need to add this change in the boiling point to the normal boiling point of water, the solvent. And we know that the normal boiling point of water is exactly 100 degrees Celsius. So we just add that to 0.956 degrees Celsius to get 100.956 degrees Celsius as the new boiling point of the solution. And if we recall from the word problem, that is exactly what we were supposed to get, so we know that that's correct. The third and final component of this problem is going to be solving for the osmotic pressure. We know that the equation for osmotic pressure is equal to molarity times R, the gas constant, times T in Kelvin. T is temperature. And we know that R, the gas constant, is always going to be equal to 0.08206 liters times atmospheres divided by moles times K. So what we can first do is solve for the molarity of the solution. And we know that molarity is going to be equal to the moles of solute divided by the liters of solution, which in our case is the moles of sodium iodide divided by the liters of solution. And we know that the moles of sodium iodide is 0.5090 because we calculated that in the previous part of the problem. And we know that the milliliters of the total solution is 576. And so all we need to do is multiply that value by the conversion factor from liters to milliliters, which is 1 liter per 1,000 milliliters. Once we divide the numerator by the denominator, we're going to get 0.8837 molarity. So now we can solve for the temperature in Kelvin. And we know that the temperature in Celsius is the boiling point temperature that we just calculated in the previous part of the problem, 100.956 degrees Celsius. And we just add the conversion factor to Kelvin, which is 273.15, to get 374.11 kelvins. And now we can plug all these values into this equation to solve for the pressure. So that is going to be the molarity times the gas constant R times the temperature in Kelvin to give us 27.1 atmospheres. And if you'll recall from the word problem, that is exactly what we were supposed to get, so we know that is correct. And if you're worried about the units canceling out, recall that molarity is moles over liters, so we have moles in the numerator here and moles in the denominator here, liters in the denominator here, liters in the numerator here, so those are all going to cancel out, leaving us with just atmospheres, which is the units of the final answer. So in this problem, we have solved for the mole fraction of the solute, we have solved for the boiling point elevation, and we solved for the osmotic pressure of the solution at that boiling point that we calculated.